current situation regarding power, kind of around the world, but in particular here in North America, is that the human populations are starting to move around, and there's going to be a great deal of urbanization. And on top of that is this trend towards electrification of just about everything in our lives, including personal, commercial, and public transportation. And with this, of course, comes a great deal of pressure on regional and national power grids. So many people are kind of turning to look at localized electricity production as well as management, and in particular in buildings, because this seems to start to suggest that we solve some of these impending problems. On top of that, of course, is the fact that we're moving into this fully digital world. So the combination of some old technology and some new technology, similar to the way the information world was transformed with the internet and all of the digital information technologies around the world today. The history, though, is interesting to look at as a guide, perhaps, to what the future solutions might be. And when we look at the history, we find out that the Rural Electrification Act of 1936, which was part of the FDR administration's New Deal, really changed and transformed the electrical world. But prior to that time, and actually prior to 1950, about 90% of America was supplied with electricity from the grid, while the rest of the country was supplied electricity off of what we now call microgrids. The interesting fact is that those microgrids in rural America eventually disappeared because they were never interconnected in any kind of a network like the AC was in the grid. Of course, we marvel at the grid today in the sense that it is one of the largest machines and perhaps the greatest machine ever developed in the world. But be that as it may, the grid took care of all of our electrical needs for darn near 100 years, at least 75 years. And that meant that the rest of us could go to sleep while a relatively small cadre of people took care of all of our electrical needs as we went along. But more recently, we've actually run into some issues. The infrastructure that we have is a bit cumbersome and imposing, and with the increase in electricity, particularly as forecasted to be needed for the electrification of transportation and continuing electrification of our digital world, that presents a problem. We also have had an overdependency on fossil fuels. And although there have been some improvements with a greater use of natural gas and to a certain extent nuclear energy, still there are many basic fossil fuel plants that are operating today in the majority. And as I mentioned, the infrastructure required to grow this system is a bit imposing, and there's a lot of resistance to doing that, expanding transmission lines or underground pipelines, etc. And last but not least, and probably the one that's most talked about, is the influence of resiliency, or lack thereof. And whether it's man-caused or natural, this poses additional problems, of course, for the grid. So we've been having these issues, and with the grid being built over 100 years ago, at least started 100 years ago, our grid operators have been pretty good at maintaining power for us, but the data suggests that that's not going to continue, and in fact, power outages and the implications of power outages are a growing and maybe even considered major concern. But if we're going to solve this problem, we may need to use some new thinking, or at least some borrowed and old thinking is combined with some new thinking, because we're not just simply going to be able to put Band-Aids on the technology that we've used for the last 100 years and expect to have a new result. So the one notion that's gaining a lot of popularity and a lot of attention, just looking at the number of hits on the internet for the term microgrid, and it's absolutely exploding. The notion here is to couple these AC macrogrid that we've operated and invested in over the last 75 or so years, and couple it together with some of the concepts around microgrids. And more, we discover that an easy way to integrate resources in a microgrid is to use DC power and couple the elements with DC to eliminate the extensive electronics that are required for synchronization and frequency control and things like that. So fortunately, we have a lot of new technology to accomplish that. So if we take the existing grid, add some smarts to it, particularly in terms of preventing linear dynamic failures or rolling blackouts that occur, and combine it with some technology at the local level, the building level, in particular in microgrids, and most notably DC-coupled microgrids, we really have something that really shows some promise for the future. It gives us not only an environmentally more favorable approach to energy and electricity in particular, but also one that shows now improving and increasing economic viability, maybe to the point where in many cases microgrids have reached grid parity in terms of cost. So if we do that, it looks to be that we would end up with a more sustainable kind of grid of grids, or as some people would call it, a mesh network. The idea here is very much like we experienced in computing, where we had personal computers that got coupled together in local area networks and ultimately in wide area networks and metro area networks all the way up to the internet. The notion is to kind of look at doing the same with power, and that is start with power generation, storage and loads and such in buildings or at the building level at the first tier of this grid of grids, and then slowly integrate it up into networks that would be like neighborhood networks and then community networks, regional networks, and on up to the macro power system, the so-called grid. So the good news is this isn't a thought process at this point. It's actually something that's happening. It's underway. Although not everybody has seen all of the indications of it yet, we are definitely in an evolution, at least an evolutionary process to get this grid of grids underway. Some would say that it's accelerating and therefore it's going to really turn into a kind of a revolutionary thing, much the way personal computing got into the internet or cell phones took over the telephony domain. In any case, the idea here and where the building comes into such significant importance is that it really is the basis for this new network or mesh network of power. So much like we fought over back in the day about the dumb terminals and smart terminals with information and computing, the idea of having intelligence at the terminal, or in this case at the building, that can assist in the not only generation, collection, and use of technology, but also the sharing of it throughout the network is probably a concept that we should pay a lot of attention to at this point. So as the grid is getting smarter and DC-coupled microgrids are evolving more and more to be distributed at building level, we're making progress. Just a quick look at how that all comes together, and that is to look at what's involved in a microgrid very briefly, and these are microgrids that will start at building levels that Paul's going to talk about in a few seconds here. You have local sources of energy, some of which you'll harvest right out of the local environment. Energy storage, which buffers that power so that it doesn't have to be instantaneously dispatchable like rotary generators have to be engaged. You have a management, and that's the intelligence and part of what ties into the whole IoT world. And then there's a way of utilizing that power in new ways, and Paul's going to talk a lot about that, and down onto the types of loads and the change in the types of loads that are occurring. So the way this evolution started was that people started tying in PV arrays and solar into power systems and then converting it to AC power and just delivering it to the local loads. Along came some feedback capability, so you could actually feed it back to the grid if you synchronized it properly and you agreed to the terms of the grid operator. Found out really that only solved part of the problem of local generation because it isn't dispatchable power. So what do you do when you have critical loads and you want to have ready standby or contributory power? You had to engage storage. And fortunately, that evolution of technology is rapidly taking place and costs are coming down quickly. Then on to looking at, well, once you have natively DC power generation and natively DC power storage, can you feed that power directly to natively DC loads, particularly IT equipment, IoT equipment, and other loads that more and more are moving from natively AC apparatus to DC. Although in most AC apparatus or in most equipment today, we have power supplies that do the conversion. But that's a conversion that has to take place at every piece of equipment and adds complexity and cost to the equipment as a result. There's a growing array of sourcing of power beyond solar and wind, geothermal, electrothermal. There's fuel cell technology, combined heat and power technologies really make sense where you have a use for the heat. And by mixing those together, you get a lot of complementary results in terms of cost savings and peak shaving and ramp-ups and black starts and things that really make sense in terms of both operational strategy as well as cost. To fully IoT integrate all of this equipment is the key, and that's where the whole IoT world comes into this, in the sense that every piece of equipment then can communicate, whether at a peer level or through a hierarchical control system. And there are yet more things to come in this whole world of local power and distributed renewable power and such. And one of those things is something called digital DC or digital electricity. And I think perhaps Paul will touch on that. The end game, though, is to create this grid of grids, which is really a mesh network in buildings that then extends out to campuses, communities, neighborhoods, as I mentioned, all the way up to a full-blown grid of grids implementation. So the attributes that we would see there that are going to change from what exists today in our power system, and you can see this mirrored in what happened in the information world. Just like most information now is created at the fringe of the internet, most power will be generated at the fringe, meaning in buildings or around buildings. New generation storage and loads are natively DC, so that means a greater use, a greater attention needs to be paid to DC, because it does provide non-synchronous DC coupling at the local level, which minimizes the whole disruptive impact of distributed resource integration into the AC grid that we have. Configuring this in a kind of a mesh topology allows us for it to be self-healing and self-configuring, which means it can avoid the kind of linear dynamic hard-connected failures that you see today in the AC system as it currently sits without support. Also, this notion of semi-autonomous distributed control supports the notion that we could have this kind of tiered transactional management structure that involves layers of grids in the grid of grids, and also enables a whole new set of business conditions which, among other things, will enable something called energy as a service, which is a way of differentiating energy not just on a cost per kilowatt, but on a cost of a kilowatt over time at a certain quality level at a certain place. So that's going to change the whole business world. But I'm going to turn it over to Paul to give his look at what's happening literally in buildings and in particular with DC microgrids. Paul?
Yeah, thanks, Brian. I wanted to share with the group an overview about the state of DC microgrids in the commercial market today, giving some examples about the loads they support and the loads that are on deck to be supported. I think it's fair to say that there are some great examples now in the marketplace where there were very few before. Here in the U.S., that's a picture on the upper right-hand corner of the American Geophysical Union, the organization for natural scientists headquartered in Washington, D.C. They've done a wonderful job of blogging their building, building.agu.org, if you'd like to look at it. And it shows their work to produce a net zero energy building retrofit in an urban area. We believe it's the first one of its kind in Washington, and it's fascinating if you're in the neighborhood. They're very proud of what they've done. And part of that is a DC bus architecture for the building that allows on-site power to be integrated into the building loads, which they have unmasked lighting controls and the outlets at the workstations for the staff. Fascinating example. Below that is a manufacturing facility out in the Midwest. We did a couple 100,000 square feet with a 380 volt DC bus that is powering DC lighting direct. So they're avoiding those conversion losses. And as we'll see, lighting really abounds as the first point of major market uptake, but it's not the only one. I would like to take a minute. This is something Brian touched on. It's kind of implied, but it's sort of hard to see. And that is how the nature of these DC microgrids in buildings actually lower the necessary infrastructure to support the building's load. So in this example, you see, imagine 100% of a regular building and its need for AC circuits to support what's going on inside. And imagine, as we've demonstrated, you could look-see, you wouldn't have to imagine, that you can actually reduce the number of AC circuits required to support the equivalent amount of lighting in the building. So you'd have the equivalent foot candles on the floor, but you actually get to reduce the number of circuits needed to support those DC systems. And this is in large part because of the development, maybe maturation of the LED light source, but also the direct current nature of that light source, which allows you to put in a power infrastructure to support it in a more modular fashion instead of in the AC model having to really put in more capacity than you're designed to today. Now, likewise, we see the same reduction in AC circuits required for direct current outlets. Unlike the USB ports you might have seen at the airport that are nestled in within an AC receptacle, those are a product of a local conversion of AC to DC. These DC networks and buildings are now running all the way to the plug, and we've seen now Class 2 outlets that can go into a building with lower capacity than an AC outlet, about half capacity, but it turns out that's better suited to the load and how it's been changing. Yeah, an example of that. First, even farther back, to stand farther back from the model, and this furthers Brian's comments about the synchronous system versus the asynchronous system that direct current represents. If you look at that top chart, thanks to our friends at the Commonwealth of Massachusetts, you'll see what's commonly understood as what utilities need to plan for in their load model, which is covering the peak. And in designing their systems to cover that peak, they wind up, as you can see, with a lot of capacity that's unused in the greater number of off-peak hours in the system. We've overcome that with a regulated utility market that provides incentives for the utility to build in excess of that peak, but it still, at the end of the day, represents an inefficiency. So consider that graph in your mind as you wander down to the bottom of the page, which is from a battery energy storage system provider showing how having integrated storage near the load and indeed solar, not coincidental that both of those are inherently direct current devices. Batteries store and discharge it. Solar panels inherently produce it. And you can see that instead of reaching up to cover that capacity required in a synchronous model like we have at the top, instead the DC platform allows the power sharing to occur closer to the load, letting us fit better the load to the source. There, now I'm going to whipsaw you going all the way from the largest macro view of the utility to what's going on at your outlet. This could be your outlet in your kitchen, but instead it's my mother-in-law's outlet in her kitchen. And I was interested to see that of the 2, 4, 5 plugs that are plugged into that duplex outlet, they're only supporting 40 watts of load. So you've got lights with LED bulbs in them, you've got a battery charger, you've got a clock radio, and all those things together amount to 40 watts. But what did the designer of that receptacle call for in the infrastructure needed for its support? Well, it's about 180 watts of capacity for every duplex outlet. And yet, when you look at all of the plugs trying to get a piece of the action there from the outlet, it is in fact 78% underloaded in terms of the receptacle's capacity. So why do we have this mismatch? Well, there are a number of reasons, but the largest one is the increased efficiency that we've been seeing in all of our devices. Maybe when the code first anticipated the need and use of receptacles, wall receptacles, maybe they were planning on standing lamps of 60 or 100 watts, but it's just not what's out there today, and indeed all of the loads that surround us have been shrinking. But by and large, our electrical infrastructure has not. Until now. That's a picture of a DC outlet, which, as I described before, is being connected to a DC bus in the building. And so you're able to get all the benefits of the interoperability of that bus all the way down to your plug loads. And I don't know if you can see, this is a prototype we made with a clear faceplate so people could get a look at what's inside, which I think is a little hard to do. But up top, there is a USB-C connector. USB-C, you're probably aware, can deliver up to 96 watts of power through that small connector, which is smaller in dimension than the two connectors below it, USB-C-A connectors we're all familiar with as how we charge our phones. And that connector has shrunk. It's gone from something that is easily seen there to something smaller, and yet the power delivery capability has grown. Also, intelligence. They now can provide full broadband connectivity in addition to the 96 watts of power in that USB-C connector, which has really changed the game for what's available in your wall socket. So after that quick trip to the utility level all the way down to the plug, I'd like to just reflect a little bit on the main load that DC has infiltrated as a supported load, and that is lighting and control systems. I guess it's been 5 or 6 years now that the LED market has really completely taken over the fluorescent light source market in the commercial industrial space and in many of our homes. Some states have already ruled, pardon me, the incandescent lamp illegal, but certainly many people are finding even fluorescent is less convenient than the LED lamps. All of these pictures are showing you commercial office buildings, manufacturing plants. There's a truck depot, Class A office space. There's a hospital, a medical clinic, and there in the lower right, that's one of the temporary office space companies, which has been growing so quickly. All of these applications have a great use for the DC platform for reasons, the top of which are cost. Today, these systems are going in at a lower cost than conventional AC systems when you count the control element. And this is why we now have national companies that are specifying DC platforms for all of their buildings. So I would say largely lighting and control is in the lead, but there are some other loads in hot pursuit. This is a picture of our flagship product. It's a DC power supply that has 16 channels out, and you can get those low voltage channels out in a number of ways. I'm going to be talking about PoE, power over Ethernet, in a moment, but we've been in the market long enough to have been early and seen its development, and we're pleased to have attracted the Vision Award from FacilitiesNet for that microgrid controller that, for the most part, is replacing the lighting panel in a building, which is part of its value proposition. But more about the load. That is really where the action is and where the greatest efficiencies can be picked up in the lighting platform, whether you're doing sophisticated daylight emulating fixtures or utility fixtures in a large space. Either way, you can save money by avoiding that driver inside the fixture. Many of you may remember the ballast, even the electromagnetic ballast that used to live in all of our fluorescent fixtures. That has shrunk in the general use of LED systems to a small driver, maybe as big as a deck of cards. And now, certainly in our case, we're specifying fixtures that have no driver at all. This removes that point of failure and also lowers the cost of the fixture, which is a big contributor in making these systems commercially competitive. It's hard to underestimate the value of controls. I think people are generally aware of the rule of thumb that a good control system should lower your operating cost of your lighting system by half. We found that true. But also, for us, the excitement is that we can talk to more than one protocol, whether it's wired or wireless. We can bring it into this DC platform at a lower cost than bringing those technologies into AC systems, because they are essentially separate in an AC platform and have to be installed separately and commissioned separately, whereas today we can ride those electronic control systems right on the back of the power, allowing us to install them simultaneously with the power installation for the load that's addressed. Retail stores, grocery stores, clothes stores, they have more monitors and screens everywhere you go. And one of the largest grocery retailers has announced plans to put a 4-inch high, 4-foot wide video screen, you can see there in the top picture, in all of their stores that would replace the paper shelf tags. This, of course, will give them an incredible advantage in terms of pricing flexibility, where they can control the image on the screen from a central location, avoiding a 2-week turnaround for changing paper shelf tags. So it's not just lighting and control, it's not just the monitor or screen, but it's the whole integrated database of what these systems support for different kinds of customers. We were happy a couple years ago to get recognized at NeoCon, which is the big interior design event held annually in Chicago, on account of the work done by our friends at the Falcon Group. They make sound attenuating panels. And so this is an example of one of these unexpected channel partners that have created a new way of embedding lighting and control into sound masking devices or sound attenuating panels. And the creative way they were able to do that attracted them a gold award at NeoCon. I did mention the DC outlet. If you consider all the different places where you might use that, work comes to mind, where you plug in a laptop or a monitor or charge your phone, all of which are looking for a DC input, and that's true. But one of the exciting applications for the DC outlet that we found is in healthcare, hospitals, and health clinics, in that they are generally required by their regulators to have medical grade receptacles in all of their locations for a couple of reasons. One, for safety. You want to have that ground fault interrupter embedded in all of the receptacles in a healthcare facility, but also for the pull force of the wire coming out of it, so that you don't have a cheaply made receptacle or a poorly made mating plug falling out of the wall unexpectedly. So those two elements, which are the key to having a medical grade receptacle, are removed by having a DC receptacle that's powered by Class 2 power. And the reason for that is largely safety. Class 2 power levels being below the shock and startle hazard, as well as the fire hazard. They do not require a medical rating, and yet they can power a great many things inside of a patient's hospital room, doctor's exam room or office, and regular office and lounge areas in a hospital or clinic. So we're seeing a real money-saving opportunity in the healthcare industry for the DC receptacle, in addition to office space. Another DC load applications, and I tend to spend more time on the load than I do on the distribution method, because that is where things can change quickly, where people are specifying loads. Owners of buildings are buying loads every day, trying to come up with more efficient ways to operate. Sometimes that opportunity is embedded in the load, and that is true more and more with networked shading systems. You can see this is a graphic reflecting shades in an office environment, and by having those shades networked and working according to clock and calendar, you can be sure that your building is put to bed at night and not rely on staff to lower those shades. And if you can demonstrate that in a commercial building, you then put yourself in the neighborhood of utility rebates for those consistent energy savings tools deployed in a building. And we're excited to see that happening because it used to be only available in a very expensive platform, and we've demonstrated that we can knock a third or so off the price of that network shade solution. What's ahead? This is I think, an interesting graphic that shows a bird's eye view of where a gas station might be going one day soon. I'm sure many people look at that canopy that's always over the pumps and think solar. Well, it's not enough, but it is a start. This is an analysis we did for a convenience store and a gas pump operator of global proportions as they consider how to convert their gas filling stations to DC fast charging stations for vehicles. And you can see our proposal included a significant amount of battery storage along with the solar and the grid connection. But it also involved shrinking the load. They went from about an 8 kilowatt steady state load in that convenience store to just under 5 kilowatts by converting the loads to DC. That doesn't sound like so much, maybe 3 kilowatts in load reduction, but if you've got 20 or 30,000 gas stations, it adds up in your portfolio. We think that critical interface you can see there between the building and the power pole from the grid is where the action will be in managing these more efficient buildings and the grid. As they get more efficient on their own, as we introduce on-site DC power to carry that load, it raises the specter of being able to export power as alternating current to the grid if you have an excess of it thanks to your efficiency measures. Likewise, if you're able to bidirectionally connect those DC fast charging vehicles, which are all fast charging vehicles, take their charge in a DC format, you have this opportunity to aggregate both power generators and storage holders, elements that can provide power back in an emergency. So I think that's a really interesting element in the power systems coming up for us. Quickly to POE. We don't make, my company doesn't make POE products, but you can't ignore the advent of power over Ethernet to supply small loads. This is true for telephony. We've all seen telephone handsets that get their power through the Ethernet cable, and maybe also the video cameras around commercial buildings that also get their power and share their data that way. But the LED revolution has created opportunities also for the POE platform in lighting. There have not been wholesale conversions in locations or customers that we're aware of yet, but there have been some big projects completed, and we think it's an important trend to watch. I would say that so far, some of the early limitations on that platform is that while the installation is less expensive using low voltage wiring, the costs still have remained high. The electrical efficiency has not kept a pace with other higher power conversions, and still the big data value, this is the IoT webinar series, that big data value proposition has still not been embraced by a lot of end customers. And so it'll be interesting to see how that comes about. I promised to mention Volt Server, which is an exciting technology from our friends at the company of that name, who can deliver a Class 1 voltage on what is ordinarily considered Class 2 wiring. And I would say if you haven't heard of that, it's worth taking a look at the Volt Server website. And the promise is that they'll be able to deliver higher and higher power levels on lighter and lighter infrastructure. And so in that sense, this fits in exactly with my theme in the talk, which is lighter infrastructure is called for because the loads do not demand the same power density. And here's an example of a new technology that is providing more power over a lighter infrastructure, which we think is really exciting. That's my cavalcade of adopters around the country. I have 3 times that many logos, and so that tells me that there are great opportunities ahead for new entrants in the market, but also for facilities managers, building owners, architects, designers to explore the kind of new freedoms that are available by going this route. I believe that's about my time allotted. I appreciate the opportunity to share this with you, and you'd be welcome to find me behind that email address. That's paulsavage@nexttechpower.com. Thank you.
Paul, there was a couple of questions that came along. One was the Ford building that you mentioned. The question is, where was that, or what building is that?
Sorry, which, the Ford building in the picture?
Yeah, or the one that you mentioned.
I think I talked about the AGU building, which is the American Geophysical Union. That's at 200 Florida Avenue in Washington, or 2000 rather, Florida Avenue in Washington, D.C. The Ford building, we're in their Michigan assembly plant here. I believe that's a rendering of a Ford plant in Thailand where we're installed.
Okay, another question was about what about the regulatory or regulation of rates and fees regarding DC microgrids? And I think I'll take that one and just answer that the regulatory apparatus that governs fees and prices and so on, rates of electricity, really has less to do with the type of electricity, whether it's AC or DC, but has to do with where that electricity system is being used. So typically inside buildings, it's what they call behind the meter, which means that it's unregulated at least by utility regulation or by regulatory law in that domain. You still have commercial laws, and of course you have electrical municipal codes and so on that you're familiar with, and business codes that, consumer protection and all that apparatus to protect behind the meter stuff. I think the coming discussion, and it's already started, is what happens when you cross property lines and start to infringe on the rules that were granted to many utilities as being natural monopolies. And that's being hashed out almost on a state-by-state, municipality-by-municipality basis. Some of the more aggressive states with regard to looking at deregulation or re-regulation are states like California, New York, New Jersey, and Maryland, and so on. But other states are wrestling with the same question as the whole paradigm of power and communications changes. How does the regulatory system need to address that? So we're likely to see almost as much innovation required in that domain as we do in the technology domain for what's going on. So regulatory-wise, AC and DC don't make a difference. It really has to do with, the territory and the granting of monopolies.
And I see a couple here I can answer for Kyle Muleg. The amount of power that fast charging stations are looking for is changing very, very rapidly. Just a year ago, you could confidently say 50 kilowatts would get you there, and now there are companies in Europe providing single connectors for the fast charging of vehicles capable of 300 kilowatts at a clip. So I think before the mass deployment of these kind of technologies, gets to where it's really replacing gas, that number is not set, but you could probably assume 100 kilowatts per connection would be a good place to start. We also had from Manjot Kandura, what are the other alternatives to DC lighting sources in addition to PoE? I'd say that there's a great many companies out there with non-conforming PoE-like systems that are using structured cabling, and so I would expect to see more and more of PoE-like lighting systems in the marketplace, although we think a conventional two-conductor 12-gauge system actually gets you greater value at a lower cost. And one other thing, Christine Gibney from the American Geophysical Union, thank you, Christine, for piping up, and she points out that they are providing net zero walking tours of the building at 2000 Florida Avenue in Washington, D.C., Mondays 12 to 3 and Wednesdays 11 to 1. And you can schedule a private tour by contacting her at netzerotours@agu.org. Thank you, Christine.
And Paul, I think it's important to point out or re-emphasize the fact that with the proliferation of sensor technology and other devices that are being actuated, whether it's cameras and things that are providing what people are calling modified or enhanced reality environments and so on and so forth, that this articulation using electrical devices really begs the question of how do we get wiring to reach all these devices and so on. Some of the solutions obviously can turn to wireless if they're portable devices and can, sit down in some place where it can get a wireless charge. But the whole notion of a lighter gauge wiring system with smaller, maybe even more prolific outlets really is important. The picture that you showed of your mother-in-law's kitchen is a fraction of what you'd see in my house. I sometimes have 2 6 or 8 outlet plug strips in addition to the splitters. If you went into my office, my home office, where I have 3 or 4 printers and I got multiple screens and all kinds of devices, the way the house, my home, which is where my office is, was wired is just inadequate. The other question that was asked with that regard is the question of, is this all okay with the NEC, the electrical code? And I'm happy to say that right from the get-go, and this started a good 8 or almost 10 years ago now, we worked with the NFPA and with the UL and NEMA and others to get a lot of the early code corrected or expanded or at least redefined, because in most cases it really didn't change the basic requirements for safety, but it was hard to interpret a lot what was in the NEC because it was written, with AC in mind. So there was some interpretation that had to be done, but a lot of the code now has been expanded to include DC. So that applies to these lighting circuits and a bunch of other things where you have touch safe, particularly where you go to Class 2. There's a lot of definition in there for Class 2, and of course Class 1 has to follow the same rules of Class 1. If it's designated as Class 1 wiring, then it's Class 1 wiring, and not much changes. So I hope that helps answer that. And I know that some of the early installations, very often a local inspector would call up and ask about things. But there's been quite a bit of training that's been going on at the IBEW and NECA and so on, with the help of NEMA and others and eMERGE.